Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion with evaluating special functions. And after looking at many different special functions, we can now look at the Struve function. So the Struve functions, just like most of the special functions, are kind of the solutions of a differential equation. And for Struve functions, we have the Struve differential equation, x squared y double prime plus xy prime plus x squared minus nu squared y. So this is very similar to the Bessel differential equation. To refresh your memory, I'm going to go back to the Bessel differential equation, x squared y double prime plus xy prime plus x squared minus nu squared y. But in Bessel differential equation was a homogeneous ODE or ordinary differential equation, which means the right hand side of the equation was 0. But the Struve function is basically the inhomogeneous version of this equation, right? So the right hand side is not 0, it's 4x over 2 to the power of nu plus 1 square root of pi gamma function of nu plus half. Now, if you're wondering where this comes from, it comes from like some special cases of the wave equations, when we solve the wave equation such that we also have a source that is generating the wave, and the solutions are the Struve functions h nu and k nu, and k nu is defined by h nu minus y nu. Not surprisingly, this Bessel function of the second kind appears, and again, not surprisingly, because this is a wave equation, we expect the behavior of the h nu and k nu be kind of like oscillatory functions, right? We saw that for the Bessel functions, j nu and y nu, and here obviously y nu appears in k nu, so we see that oscillatory behavior should be there, right? Now, how do we solve this differential equation? We always use a method of power series. So we set a power series for x, for h nu of x, which is from sigma from k equals 0 to infinity, ak x to the kth power, and then we realize that all the odd powers are 0. Only the even powers and the coefficients of even powers are pretty much related to gamma functions. And we have this lead term, x over 2 to the power of nu plus 1, right? And nu doesn't have to be an integer number, so it could be any real number. So the lead term is x over 2 to the power of nu plus 1, and the series has an oscillatory behavior, minus 1 to the k, x over 2 to power of 2k, gamma of k plus 1 half, gamma of nu plus k plus 1 half. Again, very similar to Bessel function, j nu, but in j nu we had this, basically here we had the gamma of k plus 1, which was pretty much, because k is an integer, gamma k plus 1 becomes k factorial. So if I go back to the Bessel function, you see we had this k factorial. This is in fact gamma of k plus 1, right? So again, Bessel function seems to be a special case of the Struve functions, and they're very related. So the implementation is going to also be very similar, but there is a little bit of difference, and the difference here is that now we factor two gamma terms. One is gamma of 1 plus 1.5, and then gamma of nu plus 1.5. We factor these out and then construct the series, the evaluation recursively, exactly like what we did with the Bessel functions. Where was the Bessel? Here. So this series, what we do, we factor out the lead term x over 2 to the power of nu, and then we factor this gamma nu plus 1, and then we recursively construct the remaining terms, including the factorials. All right, and we are obviously taking advantage of the definition of the gamma function. To refresh your memory, gamma function is a function that is not defined by an expression, it is defined by a property, and the property is that for any complex number z, gamma of z plus 1 is z gamma z. So if z is an integer, gamma of k plus 1 is k gamma k. And the other property of the gamma function, which is part of the definition, is that gamma of 1 is 1. So if you continue this sequence for an integer, gamma of k plus 1 is k factorial, right? So knowing this, it's very easy to factor out gamma of 1.5 from the denominator and bring it out of the sigma, and also gamma of nu plus 1.5, and then recursively construct the series, right? So how to calculate the series? Factor out gamma of 1.5, which we already know the exact value is square root of pi over 2, and gamma of nu plus 1.5, all right? Also note that gamma of 0.5 is square root of pi, gamma of 1.5 is square root of pi over 2. And if you're wondering how these two are related, it comes directly from the Euler's reflection formula for gamma function. Let's go back and look at the Euler's reflection formula. So if I put so gamma of 1 minus z times gamma z is pi over sine of pi z, right? Or gamma z gamma minus z is minus pi over z sine of pi z. So what this means is that so if we put z basically minus 0.5, we end up with gamma of 1.5. Gamma minus 0.5 is equal to pi, right? So gamma 1.5 times gamma minus 0.5 is equal to pi, because z is 1 over 2 or half. Actually minus pi, because we are setting z to minus 0.5. But then gamma minus z is basic gamma minus 0.5 times gamma 0.5 is basically so first of all, if I put z to 0.5, gamma of 0.5 times gamma of 0.5 is pi, right? So gamma of 0.5, which is a positive number, is the square root of pi. So right off the bat, using the Euler's reflection formula, we can calculate the gamma of 0.5. And then we we use this equation, gamma 0.5, gamma minus 0.5 is minus pi divided by z is 1/2, so minus 2 pi. Here we can find the value for gamma minus 0.5, and then we put it back here for z minus 0.5. We find the value of gamma of 1.5. So these numbers, 0.5 or 1.5 or 2.5 for that matter, any integer, any half integer number, we can exactly find the value of gamma function. Okay, so using the Euler's reflection formula, we can conclude that the gamma 0.5 is the square root of pi, and gamma 1.5 is the square root of pi over 2. All right, and so again, just like Bessel functions, these power series is very good for small arguments, small x. For large x, we can use a large approximation or large argument asymptotic. So here for h nu, a small argument, we have double nu and double x. And again, just like Bessel functions, we're going to cache the value of gamma of nu plus 1.5, because if only x is changing and nu is not changing, we don't need to evaluate this gamma function, gamma of nu plus 1.5 each time, right? So we're checking if last nu is the last value that nu was evaluated, nu was set to, and we are checking if the current nu that has passed as a argument is very close to the previous nu with a threshold of 0.01. If it is, we just use the last gamma for the h function and then multiply by this coefficient, and this coefficient is basic gamma of 1.5, which is a square root of pi over 2. All right, and last gamma h is basically gamma of nu plus 1.5. And then the lead term also has a term of x over 2 to the power of nu plus 1, right? So we have to calculate this power. Else, if the nu has changed, we update last nu, we update the last gamma h, which is the gamma function for nu plus 1/2. This gamma 1.5 is still the same, so this coef is the same, and we update the least term. All right. Next, we're going to create this value, which is 0.5 times 0.5x, or x over 2 times x over 2, which is x over 2 squared. And then we create this sequence that's very similar to what we did for Bessel functions, recursively constructs the summation. Let me go back to the Bessel function. So we create this sequence, right? 1 minus x squared over 2 over something times 1 minus x squared over 2 over something, and all the way. And we always start from last term. So if we are evaluating for n term, it means the n plus 1 term is 0. So the last term we start from 1 and recursively calculate 1 minus something. So this is how we can construct this series in a very efficient way. So starting from n greater than 0, I minus minus 1 minus val over I plus 0.5, I plus 0.5 plus nu times the result, and the result is originally 1. So we calculate this summation and then multiply it by the lead term, and we get the value for h nu. All right. So for large arguments, h nu is k nu plus y nu, because k nu is h nu minus 1 y nu, right? And then k nu has a nice asymptotic expansion. K nu for large z is proportional to 1 over pi, the sum from 0 to infinity, gamma of k plus 1/2. 1/2 z nu minus 2k minus 1 over gamma of nu plus 1/2 minus k. And again, we can factor out gamma 1/2, gamma 1/2, gamma 0.5, which is square root of pi, and gamma nu plus 1/2 from the denominator. All right. And then note that this series has a basically, it doesn't include the cases when the phase of this complex number is pi. So if it's a real number, if phase equals pi, it means a negative real number, right? So excluding x less than 0 or negative real numbers. So this series doesn't work for negative real numbers. All right, and that's important to know, that the problem with series is that sometimes they don't converge in all the complex plane. So what do I mean by factorizing gamma function? Here we mentioned that from the denominator, gamma of k plus 1/2, we factor out gamma 1.5. And from gamma nu plus k plus 1/2, we factor out gamma nu plus 1/2. And again, it goes back to the definition of the gamma function. Recall that gamma of z is z minus 1 times gamma of z minus 1, with gamma 1 equal 1. Any function that exhibits this property, this recursive property, and gamma 1 equals 1 is the unique gamma function. So this means that gamma k plus 1/2, remember k is an integer, we can write as k minus 1 plus 1/2, gamma of k minus 1 plus 1/2. Now k minus 1, again repeat the same process, k minus 1 plus 1/2 is the first term, and gamma of k minus 1 plus 1/2 becomes k minus 2 plus 1/2, gamma of k minus 2 plus 1/2. And because k is a positive integer, eventually if we continue, k completely is gone. We end up with the last term is gamma, the last term becomes k minus k plus 1/2, gamma of k minus k plus 1/2, which is 0, right? So we end up with 1.5, gamma of 1.5. And in general, gamma of k plus a is any number. So for example, in the second term, gamma of nu plus 1/2 plus k, or gamma of k plus nu plus 1/2. A is nu plus 1.5, right? So in general, k plus a is an integer. We can expand this to eventually get rid of k. So it's k minus 1 plus a, gamma of k minus 1 plus a, and then k minus 1 plus a, k minus 2 plus a times gamma k minus 2 plus a, and eventually we end up with a sequence multiplication that leads to a times gamma a, because k is completely gone. At the end, we end up with k minus k plus a, k minus gamma of k minus k plus a. So at the end, we end up with a times gamma a, and now we can factor out gamma of A. All right. So here's a comparison with the SidePilot Special. This is the blue is Java implementation that I did, and the red one is the Python implementation from SidePilot Special. This is H0, and you see the oscillatory behavior. This is H1, and again you see the oscillatory behavior. And because these HNu and KNu, the Struve functions of the first kind, the second kind, they are the solutions of the wave equation. They should exhibit these oscillatory behaviors. And obviously, because for Bessel functions, we also had the modified Bessel functions, which they had a exponential rise or decay behavior. We can also have modified Struve functions, which, as you probably can guess, they're going to have exponential rise and fall behavior instead of oscillatory. So let's head to Eclipse and try to look at the Struve function. So in the special function project package, I have this Struve function. So we have this sequence, we have our lead term and the value, we have gamma function, last nu, last gamma h, last gamma k, and remember for gamma h, in the h nu function, gamma 1.5, we factor out gamma 1.5, which is square root of pi over 2. For the k, for the asymptotic behavior of the k, we factor out gamma 0.5, which is square root of pi. And this coefficient is 0.5 times the square root of pi. And I have this Bessel function here, and then the modified Bessel functions, and then in the constructor I initialize the gamma function, Bessel function, and modified Bessel function. All right. So this is the small argument expansion for the HNu, as we saw it in the PowerPoint slides. We are caching the value of the gamma, last gamma, and if the nu is not changing, we're not evaluating this gamma function many times. And then this is our recursive sequence, and then we evaluate it at 200 terms and multiply it by the lead term. All right. So this is HNu for a small argument. We can also have HNu in general, right? So it was a private method, so we're not exposing it to the user. For ABS of x less than 30, we use the HNu small argument. Nu of x for x greater than 30, we can use knu large argument plus ynu Bessel function nu and x, and that's directly comes from the definition. So if you have a large argument asymptotic for the knu, and then we can add it to ynu to get hnu. All right. And other functions such as basically knu. So knu, again, if x is a small argument, I already know how to calculate hnu, and then I subtract the ynu. Otherwise, I use the asymptotic equation for the knu. All right. So in the test package, I created a test class, test Struve function. So in test 1, let's go minus 25 to 25, 1000 points. I'm calculating h0, h1, h2, h3, and then creating a timer and then plotting them. So let's run this. 18 milliseconds is very fast, and you already see the oscillatory behavior. Of course, it's not like Bessel functions. So for example, let's turn the legend on. So 2f, this is h0 of x, h1 of x. So 2f is just the line width of the plots, and then this is the legend or the label. h2 of x, this is the Struve function, h function, and h3 of x. And then I'm going to render the plot and then legend on. So let's see the results. So this green curve is h3. It has a little bit of oscillation, but its behavior is more like rising very fast, right? But h0 and h1, they definitely have this oscillatory behavior. So let's export to Python. So it saves as a text file. Let's open it in a text editor, copy all the values, and then go to the Jupyter notebook and paste it. All right. So let's see. What we want here is from SidePilot Special. So this SP is basically an alias or import alias for SidePilot Special module, and we're going to call a Struve. I believe this is the let's try. So y label, let's call it hnew. All right, so we have to tell it, okay, y0 is h0. So we are plotting h0, and why is it not rendering the, okay, hnew of x, and you see we get a perfect match. And we know that y1 is h1, so let's plot that too. As you can see, we get a similar match. The oscillatory behavior is obvious. y2 is a Struve 2. As you can see, this one is kind of rising. It's not a real oscillatory. It doesn't go away or vanish at large x. And y3 was a Struve 3. And we get the similar result. All right. So this was the introduction to the Struve functions. Very easy to implement because, again, most of these special functions come from this wave equation, like Bessel functions, modified Bessel functions, and we already have seen how to efficiently implement these. Definitely not trying to evaluate the gamma function for each term, because it has 2 evaluations of the gamma function, and then if you are evaluating 200 terms, it's like 400 evaluations of gamma functions. Very expensive operations. All right, again, the way we do it in a very efficient way is to factor out gamma of 1.5 and gamma nu plus 1.5. all right, and then we cache them for nu values because they don't depend on x, they only depend on nu. So if only x is changing, we don't need to evaluate those lead terms many times. All right, so I hope you enjoyed this lecture, and I'll see you in the next one.